Srimati R. Padmavati, Head of Department ECE, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series, BSc Electronics Honours for the subject Analog Electronics. These are the topics we are going to discuss today: introduction of transistor, different types of transistor as NPN, PNP, different configurations of transistor, common base, common emitter and common collector. Before the transistor was invented, in 1904, the vacuum tube diode was introduced by J.A. Fleming. Due to the radio and television gives greater stimulation for the tube industry, the production of tubes were increased from about 1 million tubes in 1922 to 100 million in 1937. Later, 4-element tetrode and 5-element pentode gained predominance in the electron tube industry. Further, due to the rapid advancements, there is a tremendous need in the vacuum tube production. Tremendous advances in design, manufacturing techniques, high power and high frequency applications and miniaturization. This picture shows the vacuum tubes. It has two terminals. This is cathode and this is anode. By heating the cathode, the electrons will move freely towards the anode, and by giving the supply, the cathode is heated and so the flow of current takes place. The first transistor was introduced on December 23, 1947 by Walter H. Brattain and John Bardeen, and they explained the amplification action of the first transistor at the Bell Telephone Laboratories. All amplifiers will have at least 3 terminals, with one controlling the flow between other 2 terminals. So, this is the picture of first transistor. So, we all know that diode has 2 terminals, and now the transistor has 3 terminals. One terminal is going to control the flow between other 2 terminals. Here we know the formation of the diode also. So, here this is a metal base, this is N type layer and this is P type layer, above which there is a plastic and enclosed with the collector lead here and emitter lead here, and this is again a plastic. So, this is what the first transistor looks like. So, what are the advantages of the transistor over the vacuum tube? It was smaller, lightweight, no heater is required or no heater loss, rugged construction, more efficient since less power was absorbed by the device itself, instantly available for use. It does not require any warm up period and it can be used in lower operating voltages. These are the advantages of the transistor. And now we are going to see the types of configuration of transistor. So, when you look at this picture, it shows N, P, N layers, and this transistor is said to be NPN, where this P type layer is sandwiched between 2 N type layers. So, this is NPN transistor, and similarly for PNP transistor, N type layer is sandwiched between 2 P type layers, and this is the terminal, emitter terminal, and this P is base terminal and this N is collector terminal. Here in PNP, this terminal is emitter and sandwiched layer is base, and this is the collector terminal, and the middle layer is said to be base, which is very thin and it is very lightly doped of impurities, and emitter is highly doped and which is going to inject the electrons or emits the electrons to the base, and the collector is moderately doped. It is going to collect the electrons from the base, and so it is called as collector. Collector is the largest of three regions, so it dissipates more heat than the emitter or base. And we know that the transistor has two junctions. See here in this picture, there are two junctions in the transistor. Here, this is the input junction, that is the input terminal is emitter here, and base is the common terminal here, and collector is the output terminal here. So, between this input and the common terminal there is a junction formed, and in between the collector and the common terminal another junction is formed. So, emitter base junction is the input junction, collector base junction is the output junction. So, the transistor has two junctions, because the one between emitter and base and other between base and the collector. So, because of this transistor is similar to the diodes. One is the emitter based diode and other one is the collector based diode. For a diode, we know that it has only two terminals, P and N. If P and N is joined together, and if you give a metallic contact at its extreme, it is becoming a diode. So, similarly, you can imagine that this input junction is a diode and the output junction is another diode, which is, so two diodes are connected back to back to make a transistor. And now look at the depletion region of these junctions. So, we know that the depletion region will form once the PN material is joined together. So, since the emitter is heavily doped and base is very lightly doped, the concentration of the ions present in the emitter is very high, and so the depletion region of base is penetrated and very lightly to the emitter. And similarly for the collector, the depletion region is penetrated lightly to the base and heavily to the collector. And the width of the depletion layer we have seen that as 0.7 for silicon and 0.3 for germanium. And depletion regions layers do not have the same width. Why? Because different regions have different doping levels. As I said, the emitter is highly doped and this base is lightly doped and collector is moderately doped. So, the depletion width of the depletion region will vary according to the doping levels. Here the width of the center layer, that is the base layer, in this particular case the center layer is the base layer. The ratio of the total width to that of the center layer is 150:1, and the doping of the sandwich layer, that is again the center layer, is also considerably less than that of the outer layers. It is 10:1 or less. This lower doping level decreases the conductivity of this material by limiting the number of free electrons. So, it has a higher resistance. The base terminal has higher resistance because the doping level is very low. So, next is forward biasing the transistor, forward bias of BJT, which refers to bipolar junction transistor. And why it is called bipolar? Because the current is both by the electron as well as by the hole. So, it is said to be bipolar. The holes as well as the electrons are part of the current in the transistor, and so it is bipolar. There is a device called unipolar in which only one carrier is employed, either the hole or the electron. If both the junctions are forward biased, we know what is a forward bias and what is a reverse bias. Look at this picture. This is N type layer and this is P type layer, and this NP stands for the input junction. So, when both the junction, this is input junction and this PN holds the output junction. If these two junctions are forward biased, What do you mean by forward biased? P layer is given to the positive terminal of the external battery and N is given to the negative terminal of the external battery. And here also N to negative terminal, P to positive terminal. Now both the junctions are forward biased. If forward bias is given to a transistor, you can also imagine that forward bias is given to a diode here. Similarly, this side also forward biasing is given to the diode. So what will happen if a diode is forward biased? The current is maximum. So here the emitter current is maximum and here the collector current is maximum. Both will go to the base and come out of the base here. So the emitter and the collector currents are very high when the transistor is forward biased. Both the junctions are forward biased. And what will happen to the reverse biased? So you are reversing the polarity of the external battery in both the junctions, and so it will become a reverse bias of BJT, bipolar junction transistor. And we know that during the reverse biased condition, the current is very, very low, or you can say it is 0, and the minority carriers will flow during the reverse bias condition, and so it is said to be leakage current. In this case also it is the leakage current will only flow through the device, and so it is very, very low. When you measure this current, it will be in microamps, but in the case of forward biased, the emitter current will be in milliamps, collector current also will be in milliamps. This leakage current or the minority carrier current is only in few microamps or in nanoamps, and if you apply this device for a high power, low power system, then we can neglect these leakage current because it is very, very negligible. But when you apply this device for a high power circuits, then the effect of this leakage current is not negligible, because once the temperature is increased, then the leakage current will also increased. For every 10 degrees Celsius, the leakage current will increase double the time. So we have to check whether the leakage current is minimized or not. We have to give appropriate connection for the circuit while it is in high power applications. How the transistor is operating and how the current is maximum for at the emitter terminal and at the collector terminal. So here for transistor to be operated in the active region we will see it later. Now for the transistor to be work in a proper condition, you have to give the input junction as forward biased and the output junction reverse biased. Previously we have seen both the junctions forward biased, what will happen to the diode or to the transistor, and the next is both the junctions are reverse biased, what happened to the transistor. Now the input junction is forward biased and output junction is reverse biased. So look at this transistor, it is of type PNP. N is sandwiched between two P layers, and this sandwiched layer is normally base terminal, and this is input terminal is emitter here, and this output terminal is collector here. And when you look at the depletion region width, we come to know that this input junction is forward biased. So we know that during the forward biased condition, the depletion region width is reduced, and during the reverse biased condition it is increased. Okay, so this is the circuit connection for the transistor to be operated in a normal condition. It is said to be active region. So we have to analyze only the input part first, as a first case, and only the output junction as the second case now. See here, forward biased diode is only taken now. So, here this reverse biased diode is not connected in the circuit. We are considering that this output junction is not in the circuit and only the input junction is given a forward bias. So, here this is a P layer, this is N layer is given to negative terminal and P layer is given to positive terminal, and depletion region, width of the depletion region is decreased here, and if a forward bias is given to a diode, the maximum current is flowing through the diode. So, now this is a forward biased diode. And next part, if you consider, this is the next part of the circuit diagram. Here the input junction is not considered and the output junction is given a reverse bias. So, here this is P type given to the negative terminal and this is N type given to the positive terminal. If this is so, then it is said to be reverse biasing a diode. So, now this circuit is now considered as a reverse bias diode. We know that during reverse bias the width of the depletion region is increased and there is no flow of current here, but there is a flow of current due to the minority carriers from N to P. And now we can see as a whole, the circuit as a whole. So, look this circuit. Here the forward bias is given to the input junction, reverse bias is given to the output junction. The depletion region at the input side is reduced and at the output side it is increased. And now forward bias condition give rise to the emitter current. So, this emitter current diffuse to the base, and we know that base has a high impedance because the doping level is very low, and so there is no free charge here. It has a high resistance. So, very minimum amount of this emitter current will flow through the base, and this is what happened in the forward biased region condition. And while move on to the reverse biased, so this emitter current, out of this emitter current only small amount of emitter current will flow through the base and the remaining part will flow through the output terminal, that is collector terminal, as a minority charge carriers now. So, collector collects the charge carrier, emitter emits or injects the charge carrier towards the base. And so, finally, when you can consider this whole transistor as a node and apply Kirchhoff's current law to this node. We know that Kirchhoff's current law is the sum of the input currents towards the node is equal to the sum of the output currents away from the node. And now, what are all the currents towards the node and away from the node? The current IE is towards the node. We are considering the total transistor part as a node now. So, here this E, this B and this C all are in one point. So, that is said to be a node now, considered as a node now. So, IE is the current flowing towards the node. So, IE is equal to IB and IE are away from the node. So, IE is equal to IB plus IC. IB current plus IC current. So, the emitter current is equal to sum of the collector current and the base current. The base current is typically in the order of microamps as compared to milliamps for the emitter and collector currents. And this is what we have obtained by Kirchhoff's current law. And during the reverse biased condition, the collector current has two parts. It is comprised of two parts, that is due to the majority carrier and due to the minority carrier. And this is given in an equation IC is equal to IC majority plus ICO minority. For general purpose transistors, IC is measured in milliamps, while ICO is measured in microamps or nanoamps. What is this ICO? It is a reverse biased current at the output terminal. It is due to the minority carriers of the material, semiconducting material, and this ICO is similar to the saturation current in the reverse biased diode, and it is very temperature sensitive and must be examined carefully when the applications of wide temperature ranges are considered. So, now we have seen how a biasing is given for a transistor and how it works, and what is the relationship between the current flowing through the emitter, base and collector, and using Kirchhoff's current law. And what is the collector current also? Collector current comprises of the majority carrier flow as well as the minority carrier flow. So, this is the basic for the types of different types of configuration. What are the different types of configuration? We can have the base as a sandwiched layer between two other layers called emitter and collector. If so, it is a common base configuration, and if the emitter is sandwiched between base and the collector, it is a common emitter configuration. If collector is sandwiched between base and emitter, it is the common collector configuration. So, in common base configuration, as I said, base is common to the input and output sides of the transistor. Base is usually the terminal closest to or at ground potential. So, base is grounded. All the currents we are assuming it as a conventional flow, that is opposite to the electron current, or you can say it is a hole current, and it is said to be conventional flow of current. So, whenever we are seeing an arrow mark in the circuit diagram, it is the flow of hole, or it is a conventional current, it is not the electron current indicated in the circuit diagram. And now this is the circuit diagram of common base configuration. Okay, if you are ready to draw a circuit diagram of common base PNP transistor, first you have to note down which part is sandwiched between other two terminals. So, since it is a common base, the base terminal must be sandwiched between the other two terminals, which are emitter and collector. And emitter is the input terminal for the common base, and collector is the output terminal for the common base. And also you have to know the biasing condition of the transistor. We know that if both the junctions are forward biased, the current is very high, and if both the junctions are reverse biased, current is 0. Only due to the minority carriers we will have low microamps or nanoamps range of current. So, we are going for forward biasing the input junction and reverse biasing the output junction. So, this is what we have to remember for drawing the circuit diagram. So, here this is the transistor of PNP type. The emitter, the P layer is given to the positive terminal and N layer is given to the negative terminal for forward bias. And for the output junction to be reverse biased, P is given to negative and N is given to positive. Now, the circuit is over. So, instead of this rectangular box of a transistor, this is the symbol of the transistor, you have to replace it here. So, this is the symbol where this arrow represents the emitter terminal, because this emitter emits the electrons or a hole, right. So, arrow always represents the emitter terminal. If it pointing towards this bar, then it is a PNP. If it is pointing away from this bar, it is NPN. So, here you have to replace this symbol here for a perfect circuit diagram: emitter, base and collector. And we know that the current flow is towards the junction IE, and the base is grounded. So, it is away from the junction IB, and collector is the output current, IC is the collector current, it is away from the junction. So, in this way you have to draw the circuit diagram here for NPN transistor, and this is for PNP transistor. What is the difference here? So, you have to give N, P, N in the rectangular box first. So, this N gives you the emitter terminal, and this P is the base terminal, and the final N is given gives you the collector terminal now. The arrow marks always is different when you look at the PNP as well as the NPN now. So, here in the symbol the arrow is away from the bar, it represents the emitter terminal now. And biasing also, N is given to negative terminal, P is given to positive terminal. Here P is negative, given negative terminal, and N is positive terminal. So, forward and reverse bias of the transistor is given now. So, this is the circuit diagram. So, first and foremost is the circuit diagram must be drawn correctly with all the current direction in correct way. And next is, so this is the input output characteristics of the common base transistor. So, this is the output characteristics of common base transistor. Output characteristics is drawn between the output current, which is measured in milliamps, and output voltage measured in volts for constant emitter current. The emitter current is fixed. So, this is the output characteristics, and I have told you that the transistor must be in active region. This is what the active region is. Here it is cutoff region, saturation region, and active region. So, there are three main regions we have seen in the we are seeing in the output characteristics of a common base transistor. What do you mean by cutoff region? Cutoff region is when both the junctions are reverse biased, there is no current. See here, there is no current for this cutoff region. When this IE, that is the input current, is 0 milliamps, the output current is also 0, but there will be some smaller current due to the minority carriers. So, it is the cutoff region. And what is the saturation region here? It is the left part of the characteristics, and at VCB, that is the collector base voltage, less than 0. So, this is at this point it is VCB is less than 0. So, before that the region is said to be saturation region, and when you look at the graph, this VCB, if it is increased towards 0, there is a tremendous increase of the output current. Tremendous increase of the output current IC when you increase the VCB from this point to 0. This is because both the junctions, if both the junctions are forward biased, we know that the current is maximum. So, the current is tremendously increased here. So, this is for fixed values of IE. So, we have seen cutoff region which comes for both the junctions reverse biased, and saturation region comes for both the junctions forward biased, and this active region is obtained only when the input junction is forward biased and output junction is reverse biased. During this active region, the transistor can be applicable for voltage amplification. This is the main area we have to concentrate. So, the biasing is such that the voltage can be amplified in a correct manner. So, we have seen the first transistor, and before the transistor what is the electronic device for the same work, that is a vacuum tube diode, and different types of transistor as NPN, PNP we have seen, and different configuration we have seen only the common base transistor, how biasing is given for NPN common base and PNP common base transistor and also the output characteristics of the transistor we have seen. So, these are the questions, some of the questions you can answer for it. What is a current amplification factor? Draw the symbol of NPN and PNP transistor. List the different types of configuration. Explain in brief about biasing the transistor. These are the references. Thank you.